Okay, I'm recording this video since we had another remote learning day and I won't see you in person today. So in this video, I'm just going to kind of walk through the practice exam. We started talking about this in class the other day, and I just wanted to provide a little commentary over the solution set that I've provided to you. Now, in class, we did talk about problem number one and how we can convert furlongs to, furlong per fortnight into meters per second as a measure of velocity. And in our discussion in class, we did note that when we're considering significant figures, we really should report just one sig fig here. But since we have the benefit of multiple choice answers to this review problem, we see that 16.7, I think, is the desired result here. So we'll go with that for our practice test. For number two, the question was about the SI units for distance, mass, and time. And this one's an easy mistake to make, but even though gram is our measure of mass, our base unit measure of mass in the metric system, we do use kilogram in the international system of measurement. So do make sure that you select that one properly. Now in question number three, we're talking about a race where runner A begins the race by traveling due north and then hands the baton off to runner B, who runs the same distance but in a direction south of east. Now, we don't give a specific angle measure here, but south of east is interpreted to be, kind of southeasterly. It doesn't have to be perfectly 45 degrees southeast. So we have the vector displacement vectors for A and B drawn in blue here. We would like to know what the sum of those two vectors would end up being. So let's remember from our lab work that the sum of two vectors, if we add them together tail to tip, would be the resultant vector where we draw the final vector from the beginning of the initial event to the end of the final event. And so A and C, I think I would throw out right away. But B and D are common answers. B is incorrect because the red vector that we're showing here shows the vector originating from the end of B and terminating at the beginning of A, which is the opposite direction of what we're describing here. Effectively, if we had a runner that ran north and then a second runner that went southeast, the question becomes, which direction did the baton go? If we had measured it from start to finish without considering what happened in between, well, the baton started here and ended over here. The direction of the arrow matters. So in this example, we're talking about a tennis player, Andy Roddick. He can serve a tennis ball at 150 miles per hour, which is approximately 75 meters per second. Now, these two are not that closely related. This is kind of that summary that we talked about in class, how the measurement in meters per second is approximately half of what the measurement in miles per hour is. So to answer this question, we're trying to find out, how long does the opponent have to react to hit the tennis ball back. I wouldn't use the meter per second measurement here, number one, because it's an approximate value, and number two, the additional measurement that we're seeing later is a measurement in feet. So miles per hour is easier to convert to feet per second. I think that would be helpful than it would be to go from approximately 75 meters per second into feet per second. So for that reason, that's why I performed this unit conversion initially, 150 miles per hour through 5,280 feet per mile, etc. I got that down to 220 feet per second. Now, if we're trying to find out how much time that it takes for a person to react, well, we need to convert this feet per second into a time unit of seconds. Interestingly, if we had 78 feet times the reciprocal of this fraction, 1 second per 220 feet, the product of those two fractions would allow the unit of feet to cancel, and we'd be left with a time in seconds. And so I ended up computing the result of 0.3545 seconds. Now that wasn't an option here, but it was pretty close to part B, or to answer B. But if we did look at the computation over here, and if we did use the 75 meters per second value along with the conversion factor that was given to us here, we end up using the same technique, getting an answer that's remarkably close to what the answer key suggests. So while I'm not a big fan of this method, that is apparently what was used for this particular example. So in either case, 0.35 or 0.32, the both of those answers would be acceptable, and 0.32 is the closest option. And remember, on our actual test, we're not going to have multiple choice questions for many of these. So without the multiple choice options here, if you go through this first method, there would be no indication that you've done anything incorrectly, and I would still award full credit for that approach. For number 5, this is just kind of a reminder of scientific notation. 93 million miles is a 93 with 6 zeros after it. If we convert the 93 with 6 zeros into scientific notation, that would require our decimal to be placed here, 7 placeholders away. And since 93 million is a large number, we have a positive 7 reported as our exponent. So 9.3 times 10 to the 7th power. With number 6, we have an event where you're on a tricycle traveling at 10 meters per second and you collide with something. Now, the event that we're interested in is the collision itself, from the moment of impact to the moment that you come to a stop. The time that it takes for that event to occur is 50 milliseconds. And we would like to know what's the magnitude of your deceleration or acceleration during the crash. Well, we know that we come to a stop, so our final velocity ends up being 0. That's an implied quantity from the problem. Our initial velocity was 10 meters per second, and the time that it took to come to a stop is 50 milliseconds, which is 50 one-thousandths of a second. So that's 0.05 seconds. So on my formula sheet, I just use the formula. The average acceleration is the change in velocity over the change in time. Recognizing that the change in velocity requires final velocity minus initial velocity, 0 minus 10, giving us a negative quantity, divided by 0.050 is a negative 200. Now, with the question asking for magnitude, all that we're interested is the numerical quantity, 200, and that's why we'd go with D as our answer. If we're considering significant figures, however, while this number has 3 sig figs, this one only has the 1. So I would recommend that you report this as 200 without the decimal point, if we were worried about the sig figs on this particular test. On number 7, I ended up creating a small sketch here to help make sense of the problem. We have rock A that's dropped from the top of a building, but rock B is thrown horizontally from the same position. As long as we ignore air resistance and we assume ideal conditions, which of the statements is true? Does rock B that follows the curve path hit the ground before A? Do they have the same speed just as they reach the ground? Does rock B have more acceleration? Well, none of those are correct at the beginning here. The only acceleration acting on the rock is the vertical acceleration due to earthly gravitation, or gravitational pull here on Earth. So as far as vertical speeds go, they're going to be traveling the same. But since B had some initial speed horizontally, the combination of the speed, horizontal and vertical, means that rock B is actually moving faster. Rock B does have a faster speed as they reach the ground. It's just the vertical speeds are comparable. The answer D is the best answer because while both rocks must reach the ground at the same time because they're traveling vertically at the same rate of speed, and they're both traveling the same vertical distance. B travels a farther horizontal distance, but vertically, that's the portion, that's the component that we're focused on. Remarkably, both rocks will hit the ground at the exact same time, as long as we're ignoring air resistance. Question 8 is just a sneaky trig problem tossed into our physics exam. We have a mountain road that's elevating, or that has an incline of 3.1 degrees. And if we're traveling 2.9 kilometers along the road, since the road is, presumably along this diagonal and not this horizontal component, we have 2.9 kilometers along the diagonal. Angle measure, or hypotenuse, I should say, angle measure being 3.1. The question is, what's the change in elevation being the vertical distance? We have an opposite side length that we're looking for with the hypotenuse given, so we'll use the sine function. Making sure that our calculator is in degree mode, the 2.9 kilometers times sine of 3.1, which is a ratio with no unit, we end up with 0.1568 kilometers, or when converted for meters, 157 meters. Now with number 9, there are a couple different ways that we can answer this. From the algebraic perspective and our definitions that are given to us in our formulas for this unit, we're reminded that the average velocity is an object's change in position over time. Now I'm using S for position if we ignore directionality. Otherwise, I could have used the letter X here. So the position at 1.5, now it's kind of hard to answer that as a single point in time, but if we look just to the left and the right of that 1.5 position, we see that position itself isn't changing. We've stayed at this 10-meter location for that period of time around that 1.5 timing. So if our position itself doesn't change, if zero change in position is divided by some change in time, we do end up with a velocity of 0 meters per second. Now, a calculus student would recognize that our position function over time, we would just take the derivative or the slope of the line at a given point and note that the slope here is 0 as well, and also would indicate that there is no velocity at this moment. The benefit goes to the calc students because they recognize that the steepness of any line of a position over time function does give us the velocity. So all they need to do is calculate the slope of any of these straight line segments. Even if they were curved line, a calc student would compute that. But for you non-calc students, that's good to know as well, especially if we have these nice linear position functions. With question 10, I do like this one. We have a projectile motion problem. There's a theoretical component that helps us answer this question. So initially you might note that, okay, at impact, the ball is launched at 40 degrees and its diagonal initial speed was 55 meters per second. But what we have to recognize is that as a ball moves in free fall, as it goes along this projectile motion, provided we have no air resistance and we're in these ideal conditions, the horizontal speed component of this diagonal speed remains consistent throughout the duration of the flight. There is no horizontal acceleration experienced. So if we can compute the horizontal component of this diagonal vector, then that horizontal component will be used at the top of the path as well as the beginning and anywhere else along the way and even at the end. So as a reminder, let's see, I can't do this with my mouse. I don't have my pen right now. The vertical component, if we had stacked it over here, we'd have ourselves a nice right triangle to solve. The horizontal component of the right triangle is computed using cosine. So the hypotenuse length times cosine of 40 gives us about 42 meters per second. So when we're worried about the horizontal speed at the top of the path, or anywhere along the path for that matter, we recognize that the speed is 42 meters per second. Now, if we wanted to know the speed of this ball anywhere else along the path, anywhere other than at its peak, well, then we'd have to worry about the vertical component that goes with it. At the beginning, the vertical components are getting smaller, and towards the end, the vertical components start getting larger. And we have to combine those vertical components with the horizontal components to find the true diagonal speed. On number 11, we're talking about a frog that jumps vertically and encounters no air resistance. So we're in this ideal situation. The answer options are making you think about acceleration and how that's experienced by the frog throughout. So even though the frog leaps upward and has some velocity, eventually the velocity comes to 0 and then the velocity increases on the way down. This isn't a question of velocity, it's a question of acceleration. What sort of acceleration is being experienced? And acceleration is a quantity separate from velocity. And we'll note that through the entirety of the event, the frog is experiencing the same acceleration, 9.8 meters per second squared downward, or negative 9.8 meters per second squared. For number 12, we get back into some computations. An armadillo was startled and leaped straight upward in the air. The maximum height that armadillo was reached took 0.33 seconds to arrive there. Now, we don't know how high in the air this armadillo did leap, but we know the final velocity at the peak of that jump is going to be 0. So we have a vertical velocity that returns to 0. We don't know the initial velocity, and that's precisely what we're looking for. We do know that in the vertical sense, we're experiencing acceleration of negative 9.81, and the time that it took for that event to complete was looks to be 1/3 of a second. So if we use the formula from our formula sheet, I believe we called this one the general position function, or maybe we don't call it that, I forget its name. But the final velocity is equal to the initial velocity plus any acceleration experienced for a duration of time. We'll substitute in the known values and solve for V naught, although these days I prefer to solve and isolate for V naught first. We'll isolate V naught first and then substitute our quantities in. That way, when we perform our dimensional analysis, we can verify that our solution should be reported in meters per second. In this case, the number does come out to be 3.24 positive. Even when we account for all of our signs, that ends up being a positive 3.24. And that's a good indicator because positive 3.2 meters per second in the vertical direction does mean that this armadillo jumped upwards. I like number 13 as a question too because it really challenges your understanding of the formulas and the interpretation of what's happening here. We've got an object that starts from rest where they have an initial velocity of 0 meters per second, accelerates uniformly, and we know that it moves a distance of 2 meters and it took 1 second to complete that change in position. And I get a lot of students that think, well, if the initial velocity was 0 and now we know that it traveled 2 meters in 1 second, so it must have had a final velocity of 2 meters per second, can we use that to compute acceleration? And I caution you against that because the velocity during the duration of this event is not constant. And if we were just to take two elements of those velocities and find the average of them, that's not going to necessarily help us compute the acceleration correctly. So what we did here is we ended up using this formula from our formula sheet, that the displacement is equal to our initial velocity times time plus half of our acceleration times time squared. The initial velocity was 0, which allowed for this component of the equation to disappear. And now when we isolate A by multiplying both sides by 2 and dividing by t squared, we now have a formula that we can substitute our known quantities in, and we obtain a proper acceleration of 4.0 meters per second squared. Number 14 is kind of interesting because there are 2 answers, and the question itself does remind us that more than one statement may be correct. The average speed, now speed is a little bit different than velocity. Remember, speed doesn't account for direction. The average speed can never be greater than the magnitude of the average velocity. Well, that's a little bit hard to digest at first, but if you break it down into pieces, it starts to make sense. Remember, speed accounts for the pathway that a person took. So if a person ran out and back, their speed is accounted for over the total distance they traveled. So the total length of these red arrows, for example. This blue arrow, on the other hand, is the measurement from the object's starting position to its ending position. That blue arrow is what's indicating our velocity. So velocity in this case, if I traveled this distance in some amount of time, well, that's a very small velocity. But if I traveled the red distance in the same amount of time, ended in the same location, then the speed would be much greater than the velocity itself. The speed, we have to cover this total red distance in a unit of time, but for velocity, we just travel the blue distance. That's all that we're interested in. So velocity accounts for just the beginning and ending portion of a event, whereas speed accounts for the entire pathway during that event. So A, no good. There's a perfect example where we've just disagreed with option A. And similarly with question D, if the average velocity is 0, that effectively means that this arrow, let's see if I can do this, has no length to it. Well, then that means that the average speed must be 0. But that's not true because the average speed, if I had this situation where I traveled out and back to the starting point, the average speed is pretty significant. We traveled a large distance over a certain amount of time, but in terms of our velocity goes, we had zero displacement with the same amount of time. So we can have a zero velocity, but a much higher speed. So it's not necessary that the speed must be zero if the velocity is zero. If we had reversed those phrases, that is true if the average speed is zero. So if we have no distance traveled over a certain amount of time, then the velocity must be zero. That's true. Velocity would account for direction, but if there's no movement at all, then there's no velocity at all either. And then also in part B, the average speed can't be less than the magnitude of the average velocity. So once we determine our average velocity based on the displacement that's occurred, the speed itself, you can't travel a shorter distance than your total displacement. So therefore, the average speed can't be less than our average velocity. And so our final question that I want to talk about in this video is number 15. You've got a friend, or a cousin, I should say, named Peter, noticing a bug crawling along a meter stick. And like any good scientist, Peter noted some observations every 5 seconds. So while looking at the meter stick, he noticed that the bug was at position 49.6 at the beginning, moved down to 39.2 after 5 seconds, back up to 42.5, down to 41, and then up to 65.7. So this bug, if we had a meter stick here, appears to be starting, somewhere close to the middle, goes down to 39.2, comes back up to 42, back down to 41, and then all the way up to 65. And so, well, that's not a great representation, but hopefully you get the idea. We're going back and forth on this meter stick here. So lots of distance was traveled. We had a lot of back and forth, and you might be tempted to try to figure out, how much distance was traveled in each of these events and add them all up. But let's just remind ourselves, displacement here is a discussion of the difference between the starting position and ending position. So really, we're only interested in the position 49.6 and the position 65.7, since that's our starting position and ending position. We don't concern ourselves with this stuff in the middle at all. And we know the difference between 65.7 and 49.6 is 16.1. And it is a positive number. If we take our final number, our final position minus our initial position, we know that this bug moved with a positive displacement of 16.1 centimeters. So if we wanted to take this further, we can say 16.1 centimeters in 20 seconds of time, and we can get a velocity in meters per second if we were interested in doing so. But that's not really the heart of this question. We are literally just pointing out the difference between distance and displacement. So please don't be fooled. Okay, I'm going to stop the video here because I have a separate video that's a little bit older but still covers all of the work from 16 through 22, and I'd encourage you watching that while we're on remote instruction today. And I'll catch up with you later this week. Thanks for watching.